to show you, this is the dialysis tubing that we did in class. In our tubing, we had starch solution. Starch is too big to pass through the semi-permeable membrane. Outside the tubing, we had Lugol solution, the iodine, dropped into water. Over time, this is time-lapse. Over time, what happens is the starch, I just said the answer to this, but is the starch able to pass out of the tubing? No, we don't see any black out here. And when the iodine and the starch react, they turn black. Was the Lugol able to pass into the tubing? Yes, it's a much smaller molecule. You also would see at the end of this that if you did it correctly, your tube probably also weighed more because water also flows towards the inside because inside that tubing was a hypertonic solution. If yours didn't weigh more, it's okay. It's possible it might have even had a leak or time-wise, that day was a little crazy. But overall, that's what you should have seen happen, is that some things could pass through the membrane, some things couldn't. The evidence of this in this case would be the reaction between the Lugol's iodine and the starch. So I wanted to clarify that. All right, so something else that it's going to ask you to do in the post-lab to part 1. So if we had dialysis tubing, let's just assume for the purposes of this that water can pass through this tubing, but that in this case, whatever this solution is, let's just say it's sucrose, cannot pass through. If we put a tube of water into pure water, should we expect it to gain weight, lose weight, or stay the same? Stay the same. Because what do we call this tonicity-wise? This would be an isotonic solution. It's not that water wouldn't be moving, but it would be going in and out at the same rate, so we wouldn't expect any change. Some people thought, because there's a graph it asks you to make, that you have to make a bar graph because water's not a number. But technically, water is a number. Water would just be 0 molarity because there's no solute in there. So you can count that as your 0 molarity. What if we put 0.2 molar solution of some kind in a bag and put that into water? Should it gain weight, lose weight, or stay the same? I heard somebody say gain. This is hypertonic, so it should gain weight. So should a 0.4. So should a 0.6. But the more steep the concentration gradient, the more weight it will gain. In other words, putting one that's 0.6 into pure water should gain more weight than putting one that's 0.2 into pure water. So when you graph this is your percent change over here, you should see a graph where all of the tubes gain weight. Does that make sense? You could do the opposite experiment as well. You could instead take the tubes and put water in every tube. If I put a tube of water into a 0.2 molar solution, should it gain weight, lose weight, or stay the same? It should lose weight. What if I put a tube of water into a 0.4? It should lose even more. In other words, we could do the opposite experiment and every single one of our tubes would lose weight, in which case we might get negative percent changes. Percent change can be a positive number or a negative number. So I just wanted to make that clear. The graphs that we're going to use in this chapter are going to look a little different because in some cases, particularly the graph of the potatoes when we get to it, the potatoes, some of them gained weight and some of them lost weight. So you're going to need to have a graph where your x-axis sort of falls in the middle. And you have positive numbers on your y-axis up here and negative numbers down here. So that is something that you might see and that you're likely to see in this particular lab activity.